Welcome to the last lecture of this particular course. This could be a long lecture, but divided into various parts and things like that, so you can pause it and then basically continue watching. So this is a list of assorted topics in a very high level, and I'm not going to get into technical details. So, but the outline is something like this. We will discuss something called model predictive control. These are the various things that you can pretty much Google search and then find tutorials, textbooks for you to go further into details and things like that. And then we'll look at something called differential geometric methods, another very popular nonlinear control method. We'll provide some connections to Lyapunov stuff here, and something that we haven't considered at all, basically hybrid systems and digital control. And then the last three are kind of the latest topics. There's nothing latest about some of those things, and it's been there forever, but at least because of the ability to solve them through high performance computers these days, we actually have some way of addressing that, right? So let's take each one of these topics and then basically discuss this, mostly words. But what is model predictive control? We'll talk about what it is and then basically talk about applicability of that, right? So I'll take a bad example and then basically slowly I'll take this example simply because it's easy to understand, but where it is applicable is very different, and then those models are not as common, and therefore we don't discuss that. Suppose we have a flight control problem, and your airplane goes from one place to another. It goes through many different phases of what do you call the equilibria, right? Each geographic point has its own dynamics and things like that. So you have this particular problem of controlling where the airplane itself is constantly moving, and then each point can be treated as an equilibrium point, and we want to stabilize around that, right? So we didn't really discuss time varying systems that much, and then basically we can generalize the theory where the equilibrium itself is actually a time varying function. So in a way, that's what all the tracking problems are all about. So it's not like something exotic, it's actually the standard problem. What model predictive control does is something like this. So I'm going to solve this particular problem, f of x comma u, okay, and I'm going to have to minimize this particular cost. And by now we know how to solve this, right? I mean, if you recall, basically essentially we just in the previous lecture itself we said this is essentially trying to solve something like the Lagrange parameter problem, if I'm not mistaken, depending on the convention. So we have these equations coming from your calculus of variations approach or the Hamiltonian approach, Bellman's principle. All of them will eventually boil down to the same thing, right? So we know how to solve these, right? However complicated it might be, shooting value problems and things like that, all those methods can be applied and then solved, right? But the technique of moving horizon, or it's also called as receding horizon, model predictive control, and it's also called receding horizon. It has other names, but these are the most popular ones. What they do is they solve this particular problem, and they know exactly what needs to be u, and then they implement it from 0 to delta t, okay, the first time step, and they come here and then solve the problem again from here till the end of time, right, t in this particular case, and apply this one for the next delta t, and then do the same thing again and then again and things like that. Now those of you who paid attention carefully will immediately remember the Bellman's principle of optimality that says something like, or the dynamic programming principle it's also called, essentially says that basically if you have an optimal path and if you actually implement the optimal control for the first step, when you reach the second step from there, the optimal path should not be different from the previous. So in that sense, this seems like a useless thing to do, and why should you repeat the problem if what we are trying to do is has not changed. The problem is basically most of the time there will be small changes in f and things like that, and then the model predictive control approach essentially tries to solve that aspect of it, right? And proving a theoretical stability for this stability and optimality and things like that for this approach from a very generic theoretical fashion is still not there, in my opinion. It's not perfect, but industry people use this constantly, and this is a very popular approach. So essentially it's a combination of not a combination, but it's simply application of your finite time finite horizon optimal control problem to the case where we have sort of some dynamics is changing slowly, and then therefore I can apply this method over and over again. But at this time I'm going to assume that I know the entire this thing, and then solve the problem and then apply it only for some time. Now I'll explain a completely different scenario where this works very well, and then it can actually theoretically shown to be a valid principle. Is we were working in basically problems related to minimizing portfolio minimizing some risk of a portfolio in the stock market, and it's completely uncertain, right? And a lot of stochastic things are there in the entire problem. So we solve the problem at a particular time, expecting something to happen, right? You have an expected model, you have a stochastic model, you have a stochastic differential equation typically in that particular case, and you solve the optimal control problem. When it comes to stochastics, basically the optimality is on the expected values and variances and things like that, but not exact values. So what happens is basically when I implement this particular optimal control law or optimal strategies to minimize the portfolio, after one step I would have actually accumulated more information, right? More information from the actual path, right? So the stock value changes actually in that particular day and things like that. The next day I'm going to use this new knowledge. It may have moved really up or down and things like that. Using that new knowledge, I'm going to re-optimize from the starting point, and then again hope for I mean from there you will have a different set of paths, and then you minimize or maximize the utility or minimize the cost of this particular process, and then solve this particular problem, implement the new control law, go to the next step and things like that. So there it makes perfect sense, and it's a very valid approach to do, simply because everything is stochastic, right? So model predictive control, when it is applied to industry, it has that kind of logic, but then typically it's not stated as a stochastic optimal control problem. But if you state it as a stochastic optimal control problem, it actually becomes quite sensible to do, right? So but the nice thing about that is basically it's a matter of solving your optimal control problem over and over again. Solving stochastic optimal control problems is not that simple. Of course, as we have seen, it's not even simple if you have these shooting value problems. So the second topic that we want to do is shifting complete gears, something called differential geometric approach. Now we have spoken about feedback linearization. Okay, feedback linearization is essentially if I had something like f plus gu, can I basically do something like g inverse times minus f plus kx or something like that, right? So when I do that, I will end up with my x dot equals minus kx. The closed loop system becomes linear, right? The question is basically, can we actually put our system into feedback linearizable form? We also saw in the last couple of lectures, basically we saw a problem something like f plus g times x hat, and x hat dot is equal to u. Again, you can have slightly more complex one. So the question is basically, can we put all such our systems into this format or not, right? The answer is not straightforward. Not everything can be put into these forms and things like that. But there's a very generic theory that you know, goes back to differential geometry mathematics, the mathematics coming from differential geometry, and it involves things like Lie algebra and Lie derivatives and whatnot, right? I'm not even pretending that we are going to look into this particular course, because it requires a lot more patience into going into some of the mathematics and things like that. But it has some really nice features. We did not really address things like controllability, observability, and things like that, right? And these Lie algebra and things like that provide some answers under which we can check for controllability and things like that. It's heavily based on functional analysis. You have to compute a bunch of these derivatives on your f and g and things like that, and then some rank condition has to be satisfied, just like your standard controllability and observability gramians, and then you conclude that they are observable and things like that. And once we have this observability and things like that, you can actually transform these coordinates, and then once we transform these coordinates, they typically fall into these feedback linearizable systems and things like that, right? So related topic basically is something to do with it's popularly known as differential flatness, right? So essentially, if you take a system and take an output and then keep taking the time derivatives, and then you actually get these time derivatives and do something with that, and if certain conditions are satisfied with respect to the outputs, we call such systems as differentially flat. And again, they all rely on this same type of mathematics, and all put together provides a nice framework for solving nonlinear control problems. It provides you an algebraic method to solve problem, but it doesn't really get away from Lyapunov methods. But of course, since you are transforming everything into something as simple as feedback linearizable systems and things like that, the eventual application of Lyapunov stability becomes trivial, right? So the more difficult, the difficult part is more using all this framework to put it in this, transform these coordinates and put them in a nice form that is easy to handle, right? So in that sense, the Lyapunov part is actually trivial, whereas the rest of it is actually quite powerful in terms of providing a framework to solve very generic problems, right? So typically I would call that as an advanced course, second level course after this particular course on Lyapunov stability. There's a very old book by Albert Istudori. I've met him many times, fortunately, and fantastic person. He wrote this very old book, and then still I think it's quite readable and things like that. This differential flatness, you can look at papers by Professor Richard Murray of Caltech, and it's if you have a course that is available on this particular topic, I would urge you to look at it, right? The next topic is hybrid systems and digital control, and I'll take a few minutes and talk about it. So let's think carefully about it. I will pick up a trivial example. Let's say if I have a ball that is bouncing on the ground. If you were to write a model for this, basically till it hits the ground, it's the standard gravitational model, F equals ma, or mx double dot is equal to mg, or whatever the equation that satisfies while it is doing a free fall. If it is at a spring, that's a different aspect. You will have additional components. But let's say as soon as it hits the ground, and let's assume for the time being this entire thing is quite elastic, in which case you'll have a discontinuity. You'll have a reversal of basically velocity immediately, and the system will continue from then onwards, right? So you have this model that is continuous on some particular part, and then suddenly you'll have a discontinuous part, and then you can treat that as a discrete part, and then such models, we call them as impulsive differential equations, right? And suppose if you are dealing with systems where you have some kind of discrete component determining which control to be picked or which system is valid and things like that, that also can be treated as a kind of a discontinuous operator, right? So you have this categorical set of variables 1, 2, 3 kind of a thing, and you're jumping from 1 and 2 and things like that. That can be treated through impulsive differential equations, and more generally there are frameworks that has a general term called hybrid systems, and then different people have different types of hybrid systems and things like that, right? All of them can be summarized into one single framework. We attempted to do that in our book to search our names for hybrid systems and impulsive and hybrid systems. But part of the hybrid system is like a combination of continuous and discrete systems. So so before I talk about discrete systems specifically, let me talk about the digital control part. Digital control part is also, if you have a continuous system, I'm, let's say, driving a car which behaves according to Newton's law, which is a continuous differential equation. But let's say I'm assuming that I'm going to somehow live dangerously and then just implement my feedback control only periodically, and then basically do this sudden jerks once in a while, and that belongs to the framework of hybrid systems in general. But these days we end up doing this because of the fact that basically everything is controlled by computers, and the computers understand only finite set of digits within its memory, and then it also only implements it not continuously but discretely. So you have discrete and this finiteness put together, we call it digital control. So essentially it's a hybrid systems control. But then these days we kind of take it for granted that if it is fast enough and then the memory is big enough, then it's as good as continuous control, and then we don't really worry about the gap, and then we treat it as if it is continuous system, right? So but in reality, if you actually want to truly implement some kind of discrete control for a continuous system with sufficient time gap and things like that, one has to worry about it carefully in terms of its stability, because between the gaps what will happen, right? There are things like zero order hold. What it means is I'm going to implement it at a particular point and then leave the constant control till the next step, till the time I change it. Then there are other kinds of things. Basically, I'm going to implement a linear control law between two time steps, and then every time I reach a new time step, I change my slope of the control for the next time step, and so on and so forth, right? So there are many different ideas of this digital control, and it's a combination of hardware, software. If the hardware is good enough, then we can implement things like this slope based control and integrals and things like that. If it is not, then basically we'll end up implementing purely discrete type of control, right? So so therefore it's a combination of continuous and then discrete systems, and one has to understand to some extent how discrete systems work. So I'm going to basically look at one small simple, rather a simple looking system. Xk plus 1 is equal to f of xk, right? So this is kind of equivalent to our x dot equals f. Okay, so the difference is basically it changes every step, and then basically unlike the solution to your ordinary differential equation, this is not going to be continuous. This f could take xk to some other number, and it keep jumping, one here and one here and one here and things like that. And the question is basically, we in steps can we reach the equilibrium point and then define asymptotic stability and things like that. So the asymptotic stability now and Lyapunov stability and things like that, all deltas and epsilons remain the same, except basically your whether we remain for all k, whether this is going to be satisfied as long as the initial condition is less than delta. That's your Lyapunov stability. And then of course asymptotic stability will look something like this, right? So in a way, what I'm saying is everywhere we have continuous functions replaced with the sequence of numbers, and then that gives you discrete systems, right? So what about Lyapunov functions? Well, actually the LaSalle theorem, or even before that, the limit sets and things like that, when we defined actually the time, whether it's discrete or continuous, does not matter. You know, if you actually go into the mathematics and try to understand, a lot of it is actually based on sequences that we find on the continuous time and things like that. So many of those results that we talked about extend easily to discrete systems. So there's not much for us to worry about, right? So in that sense, we still want, from a Lyapunov function perspective, v going down as k increases. So in that sense, we want some condition like v of xk plus 1 less than or less than or equal to, depending on whether we want asymptotic or Lyapunov and things like that. So but then we know that xk plus 1 is f of xk. So and then we will convert this into algebraic condition. So just like our v prime, this is equivalent to v prime f less than 0, right? So this is how it changes, and then basically if it is soft, then it implies Lyapunov stability. If it is hard, then it implies asymptotic stability. If it is soft, then we can actually explore the set all x's such that v of f of x is equal to v of x, and then find an invariant set within that to tell you whether this particular system is asymptotically stable, or maybe it's converging to some other point, some other invariant set within this particular set. So in that sense, as long as you treat v as kind of the energy function that keeps decreasing, and then decreasing is good or non-increasing is good for stability, boundedness and invariance and all those things, properties can be easily generalized, and in that sense it's fairly trivial. But when you sit down and try to prove some of the Lyapunov functions and things like that, the differences are not so significant, but sometimes can become subtle, right? So for example, you know, where we assume that the solution is continuous, and if you used continuity in any of these proofs, suddenly that is lost because we don't have continuity, right? And there are many aspects to discrete systems that are quite different from nonlinear systems, the standard ODEs. So for example, I haven't really discussed this particular thing in detail, but let's say I had a differential equation something like this, and we call that as a delayed differential equation, right? So think for a second, x dot is not going to kick in till t becomes tau. So in a way, it's going to stay dead, or for that matter, it actually is going to depend on some initial condition that is there from 0 to tau, right? So in that sense, this x dot, the actual solution is going to depend on entire function moving from 0 to tau, and then we solve that. And then therefore, delayed differential equations in say ordinary differential equations framework, or nonlinear differential equations, they are infinite dimensional problems, right? So if you want to address stability and things like that, the definitions go quite easily extend, but the subtleties involving infinite dimensional systems is quite painful, and then basically we end up with possibly making a mistake if we are not careful. Lucky for us, basically whenever we have a discrete time system, something like I don't know, theta or something like that, where theta is also an integer, because of the fact that these are all integers, the difference between this and this is going to be finite, right? And in the sense that you'll have finite number of steps in between theta and k. So therefore, this can be rewritten as actually a higher dimensional, single dimensional equation, and it never enters into infinite dimensional framework. So there are many such things that are that make what you call discrete systems easier than nonlinear systems. So the standard nonlinear system. So I challenge you to basically go back and look at many of the results and develop the discrete versions. It's there in our book, but it's nice for you to try on your own. The only thing that is very difficult to imitate is actually the adaptive control framework that I showed, and it has specific difficulties in terms of extending that, and few other things. The KYP works out, but with some very strong assumptions and things like that. So there are certain things from a theoretical perspective makes things very simple in discrete time, and in certain things, because of the fact that we have this kind of v of f of x and things like that, it makes it difficult. In the ODE case, basically you will have something multiplying something, so you have some kind of linearity there, whereas this one is non-linearity, and it makes it inherently more difficult. So if you want to seriously understand hybrid systems, then one has to understand discrete systems very well, and then after that one can venture into impulsive systems and hybrid systems and digital control and things like that. But like I said, digital control these days, most of the times we assume that the digitization is fast enough that we can survive without really any big problem in terms of instability, right?